In section 8.4, we're taking the idea from section 8.3 and from the AS course of if we have displacement, we differentiate displacement as a function of time, we differentiate and we get velocity. We differentiate velocity and we get acceleration. We're taking that idea and we're combining it with the ideas that displacement is a vector and therefore it can be written as a two-dimensional vector. Velocity is a vector, therefore it can be two-dimensional, and acceleration is a vector and therefore it can be two-dimensional. So we have this sort of situation going on. If r is 2t cubed 50t to the minus a half, then I've got r, my position, in terms of time. So what about my velocity? And what we have to do to get from r to v is to differentiate. Well, how do we differentiate a vector? You'll be pleased to hear that we just do it as simply as possible. We differentiate the x component and we differentiate the y component, like so. Okay, and that really is it. Okay, everything else that we've done before is the same. I should remind you of this notation if you haven't met it before. R dot means the derivative with respect to time of r. So r double dot means the second derivative with respect to time. So r dot is velocity, r dot dot is acceleration. But other than that, everything works the same way as it did before. So if we know r and we want to find a, then we differentiate and we differentiate again. Of course, if you do this in terms of i's and j's, then the same thing is true. Now again, personally, I prefer the column vectors. If you've got the i's and j's, then you have to remember that I and j are both constant vectors, and therefore in the differentiation they just sort of hang around and don't change. So so that's where we get the results that we get in this box here. Don't forget the speed is the magnitude of the velocity vector, so when we've found that velocity vector, we've got to substitute in t equals 4 and then find the magnitude of it. Find the acceleration, we differentiate again. F when t equals 2, well, remember, if we know the acceleration vector, acceleration is a vector, so is force. So mass times acceleration, so the mass is 0.8. We take 0.8 times it by the acceleration vector, and that gives you the force vector. But we leave that as a vector because it's a vector quantity, so we give it as a vector in a vectors question. If they ask you for the magnitude of the force, then you would find the magnitude of the vector. If they ask you for the direction of the force, then you draw yourself a little vector diagram out and you work out, if it's got this horizontal component and this vertical component, then there's the force. So that tells you the angle it's acting at to the horizontal, and if they ask you for the angle to the vertical, it's this angle here instead of that angle there. So mixing up several things that we already know and using them. Section 8.5 does exactly the same thing with integration. It works exactly the same way. If you integrate velocity, you get displacement. If you integrate acceleration, you get velocity. Just bear in mind that you add on a constant of integration, and that constant is now going to be a constant vector. The constant vector is an x and a y component. So in order to work out what that constant vector is, as they did in AS, they have to give us some boundary conditions. In other words, when t equals 0, the position is this, and whatever the position is now has to be given as a two-dimensional vector as well. So that is section 8.4 and 8.5, and that is the end of mechanics from AS level and from A level. Good luck with that. I hope it helped.